Hi statisticians. Today's notes are on discrete random variables. Let's get started. This is a photo of Las Vegas, Nevada, the gambling capital of the US. Millions of people travel to Vegas every year hoping to get lucky at the casinos and win big. One of the most popular casino games that gamblers play is roulette. In roulette, there's a rotating wheel with slotted spaces. As the wheel spins, a bouncing ball is placed in the wheel. Whichever space the ball lands indicates whether you win or lose money. So today we're going to statistically analyze the game of roulette and answer today's key question. Is there a way to beat the casinos at their own game? With that question in mind, let's move into our notes. We're going to cover two topics today, starting with expected value. There are different ways to bet in roulette, but the simplest way to bet is by color. You can bet that the ball will land in one of the 18 black spaces, or you can bet that it will land in one of the 18 red spaces, or you can bet that it will land in the one green space on the wheel. Clearly, it wouldn't make a lot of sense to bet on green, but it looks like the red and black spaces are pretty similar in terms of chances. So let's investigate what our odds would be if we bet on black. To model this situation, we're going to define a random variable, capital X. X is called a random variable because its possible outcomes are determined by chance. Let's let the capital X equal the winnings from a $100 bet on black. There are two possible outcomes for this variable, either winning $100 or losing $100. We model each of these outcomes with a lowercase x as shown in the top table here. And in the bottom row of the table, we can find the probability of our random variable, capital X, and we'll find the lowercase x as positive 100 or negative 100. Now, there are 18 black squares out of a total of 37 squares on the wheel. So the probability of winning $100 is 18 over 37, or 0.486. Find the probability that you lose $100. That happens if the ball lands on one of the 18 red squares, or if it lands on the one green square. So there are 19 ways that you could lose out of the 37 spaces, or 0.514% of the time, 51.4% of the time. Now, before moving further, let's take a moment to talk about the difference between a random variable and a regular variable that you've seen in your algebra-based classes. When you talk about regular variables, on the left, you've seen this when you're solving equations. In this case, you would get x equals 3. A regular variable like this represents a constant number. It's a number that exists, and we just have to solve to find it. By contrast, a random variable represents an outcome that has not happened yet. It could take on any set of possible values determined by chance. So rather than solving random variables, we model their probabilities. We represent our random variable, capital X, using this table. Let's start with this thought experiment. If we spun the wheel 1,000 times, betting on black every time, how many wins would we expect? Well, with our probability distribution, we would expect to win 48.6% of the 1,000 times. And if we do 48.6% of 1,000 plays, or 0.486 times 1,000, that gives us 486 expected wins. To see this in action, let's try running a simulation of 1,000 spins of roulette using an applet that's linked in the description of the video. We'll start just by spinning one time so you can get an idea. Here we have our roulette wheel with the numbers shown being red and black spaces plus our one green space. We'll spin the wheel, we'll drop in the ball, and then we'll see what we get here. Remember, we are seeing if we land on black. In this case, we landed on a red, so we lost. Now we'll move over to our simulation, and this is going to represent spinning 1,000 times. And as we go here, We're seeing which individual numbers we landed on, whether we got the green 0, the red 1, etc. And you can see that we ended up landing on black 481 times. We landed on red 494 times, and we landed on green 25 times. Getting back to our model, we can also ask if we played roulette 1,000 times, what would be the average winnings per play? So first we would get the expected number of wins and losses by multiplying by 1,000, and we would expect to win 486 times and lose 514 times. So if we multiply again by the amount of money that we would win or lose for each time, that would give our expected gains and losses. So that means we would expect to win $48,600, and we would expect to lose $51,400. And then adding those together, that would be an overall quote win, or actually loss, of $2,800. We certainly didn't get rich today, now didn't we? So to find the average winnings per play, we would divide this number by the number of plays, which is 1,000. And sadly, that means that we lost an average of $2.80 per play. What if we just calculated this expected value, or the average value per play, straight from the table? Well, that is denoted as E of X, or mu sub X. And in order to calculate it, we have this formula. What we have to do is we have to weight the individual values by their probabilities. So this notation is the X sub I. That represents each individual outcome. And the P of X sub I, that represents the corresponding probability of that individual outcome. And then the capital sigma, that means once we have each of those products, we're going to add them together after we multiply those. So for this example, what we would do for this is we would take the individual outcome of winning $100, multiply it by its corresponding probability of 0.486, then repeat that by the other outcome of losing $100 times its probability, and then we would add those two together, and we get, you can see the same answer as what we did before, an overall expected loss of $2.80 per play. So we can interpret this expected value of negative $2.80 as follows. After many trials, roulette players lose an average of $2.80 per play. And generally, this is how we interpret expected values, as the average value after many trials. $2.80 isn't a possible outcome for one spin. If you play once, you either win or lose $100. The expected value is the average over many trials, not just playing one time. Let's look at a different scenario. For a pretty high stakes coin toss, let's say if you get a heads, you win $100, and if you get a tails, you lose $100. Now, that would be modeled by this distribution. And if we wanted to then find the expected value, we'll repeat the same process that we did a moment ago. We're going to take each outcome and we're going to multiply it by its corresponding weight or probability, and then add those together. This time, we get an answer of 0. That means that this is what's called a fair game, that in the long run, it's a net 0 outcome. So let's try changing it up a bit. This time, to make it more interesting, if we get a heads, we're going to win $300, but a tail, we're going to lose only $100. Now let's see what the expected value looks like. So here's our new probability distribution. And now weighting our outcomes gives us an overall expected value of positive $100. So as you can see, now the value is winning is higher than losing, and the expected value of the game is overall a positive number. This is a game you'd expect to win money in the long run. So far, we've presumed that it's a balanced and honest coin. But what happens if the coin is weighted so that 75% of the time it lands on tails? We'll go back to $100 for winning, getting a heads, and $100 for losing, getting a tails. What would that look like? So here's our new probability distribution, and we'll find our new expected value. Remember, you take the outcome times the probability for both outcomes, and then you add up those products. This time we get an expected value of -$50. As you see here, the imbalanced probability of those outcomes puts more weight on the loss than the win, resulting in an expectation of losing the game in the long run. So now looking back at our get-rich-quick plan for Vegas by betting on black, that was maybe not such a good plan. It resulted in a loss of $2.80 per play. So clearly, betting on black was not a good idea. But how about betting on red? Well, to bet on red, we're going to check out those probabilities. There's an 18 out of 37 chance of winning, and there would be 18 black spaces plus the 1 green space. So there is a 19 out of 37 chance that we would lose. And unfortunately, we get that same probability again of winning and losing, and results in the same expected value, whether we bet on black or red. And it's all because of that one green space. That one space, even though it doesn't seem like a big deal, weighs the probability in the casino's favor in the long run, no matter which color you choose to bet on. Now, an important note, much like roulette, every type of gambling, sports betting or in the casino, will favor the casino or the organizers. But even with this knowledge of unfavorable odds, gambling can still become an addiction. And as our work shows, gambling often in the long run can lead to heavy losses and consequences. So if you ever find yourself or a friend in a situation where gambling is creating difficult consequences, please call, text, or chat with this confidential hotline for the National Council on Problem Gambling. Our other topic for today is standard deviation. We've talked about it a bit, so let's first recall that for measured data, standard deviation measures the typical distance of data values from the mean, and that sigma represents the standard deviation for the population, while S is the standard deviation for the sample. When we look at random variables, the standard deviation measures the typical distance of outcome values from the expected value over the long run. And it's denoted SD of X or sigma sub X. And it can be calculated using this formula. I know it looks complicated, but we'll break it down in a second. So recall that the random variable for a $100 bet on black, which has this probability distribution and has a expected value of $2.80 negative, looks like this. So we are going to apply the standard deviation formula to this random variable. First thing we're going to do is we are going to find the differences between each of the outcome values and the expected value. So the 100 minus the -2.8 and the -100 minus the -2.8. Then we are going to square each of those to get rid of the negative values. After that, we weight or multiply those values by the squared differences, and that gets multiplied by the probabilities of each of the outcomes. Finally, we'll add those together and take the square root to undo the squaring that we did earlier. And that gives us the standard deviation, in this case 99.96. Now we interpret that as the overall typical distance between the outcomes and the expected value of -2.8. That should make sense because you would win or lose $100, and $100 is about 99.6 away from 2.8, -2.8. So that is something that should be somewhat intuitive to us. So now that we've gotten our feet wet with random variables, let's move on to our discussion for the day. Imagine the casino's have not taken a statistics course, and they come up with this game for high rollers. You roll a six-sided die. If you roll a 5 or a 6, you get $1 million. If you roll a 1, 2, 3, or 4, you have to pay $300,000. Our discussion question is, if you could play this game only one time, would you play? Why or why not? Make sure to calculate and include the expected value in your answer. So, take a moment to do some calculations, jot down your initial thoughts, and we'll discuss it further in class. That's it today, statisticians. We'll see you next time.